Yeah. So good afternoon, everyone. Today's tutorial has been cancelled because of very few people have joined. I hope my this tutorial, the tutorial sheet and the solutions are visible, and uh, I will solve all the five problems with you. And if you still find yourself uh, with any queries, then you can just drop me an email, or you can ask me and Jayesh on Teams. So yeah. So coming to the first problem. So in this problem, we have a flat plate. So the length and the width is given to us, and it is placed in water having the upstream velocity. So here the velocity is missing. So you can take it to be 1.5 zero point 0.5 meter per second. So in this problem, we have to find out the boundary layer thickness and the wall shear stress at two different locations. So the first one is at the center of the plate, and the second one is at the trailing edge of the plate. So taking a distance x from the starting of the plate, so we have to find the shear stress at distance x equals to 3 meter and x equals to 6 meter. So in this problem, we can assume the laminar boundary layer. So now coming to the solution part, we are given all this data. So we have to find the uh, delta. So to find the expression for delta, you must have solved this Blasius solution, and for the solved for the laminar boundary layer in your class. So I will directly write the final answer, that is delta by x will be equal to 5 times uh, Reynolds number times raised to the power minus zero point 0.5. So we can express delta in terms of x. We know that the kinematic viscosity of water, we can take it to be 10 raised to power minus 6 meter square per second. And it will come out to be, so we can find the formula for delta in terms of x. So the second part of the problem is we have to find out the wall shear stress at two different locations. So we can so y will be equals to 0 because we have to find out at the wall. So we can write the shear stress as mu times del u by del y. So we can find the value of we can equate it uh, using the Blasius solution, which is the table is given in the book also, so you can refer to that, and we can find the value of the expression for tau w, which will come out to be 0.332 times uh, free stream velocity raised to power 1.5 times under root rho mu by x. So the final expression will come out to be 0.117 by root x Newton per meter square. And the unit of delta will be meter. So here the x, we have to substitute the value of x in meters. Uh, so yeah, it will come out to be at x equals to 3, it will come out to be 0.0677 Newton per meter square. And after, if we substitute x equals to 6 meter, then the tau will be 0.048 Newton per meter square. So now moving to the second problem. So here the laminar boundary layer velocity profile is given to us. So for y less than equal to delta, the velocity profile is given, velocity expression is given, and for y greater than delta, the velocity will be constant, that is equals to u, which is the free stream velocity. And in this problem, we have to show that the profile that this velocity profile satisfies the appropriate boundary conditions. So there are three boundary conditions that we have used while solving the boundary layer problem, and we have to show whether it satisfies the boundary condition. Yeah, we have to show that it satisfies all the three boundary conditions. And the second part is using the momentum integral equation uh, to determine the boundary layer thickness. So this also you must have covered in your class. So I will quickly move to the solution. Yeah. So the first one is no slip boundary condition, that is at y equals to 0, that is near to the plate, the velocity will be the velocity of water will be equals to 0. So we can find it by substituting y equals to 0 in this expression of uh, u by capital U. So we will uh, get the velocity as 0, so which satisfies the no slip boundary condition. And the second is um, at y equals to delta, the uh, fluid velocity will be equals to the free stream velocity, that is the u infinity. So here it is denoted by capital U. So substituting y equals to delta in the velocity expression, we will get small u by capital U equals to 1. So which implies that at y equals to delta, small u equals to capital U, that is the free stream velocity. And the third and the final boundary condition is that y greater than equal to delta u remains constant. So there is no velocity gradient above this point. So del u by del y equals to 0. So at y equals to delta, we can differentiate the velocity, and it will uh, when we substitute y equals to delta, so 2 by delta minus 2 by delta, so it will cancel out, and uh, the gradient will be 0. So now coming to the second part of the problem, we have to find out the first we will find out the shear stress. So in terms of momentum thickness, uh, uh, you have derived it in the class also, that tau w, that is the tau at wall, will be equal to rho times u square times d theta by dx. So here the theta can be written as integral of u by u infinity times 1 minus infinity u by u infinity dy, integral from 0 to delta. So you can like you can substitute y by delta equals to y dash, and you can just differentiate um, dy equals to, then dy will be equals to delta dy dash. So you can substitute dy here in the above expression, and the limits will change from 0 to 1, and 1 delta will come. We can come out of the integration, and you can just simply integrate it from this expression from 0 to 1. So this theta will come out to be 2 by 15 times delta. So we know that the tau w will be equal to mu times du by dy. So at y equals to 0, so at the wall. So we can just differentiate velocity with respect to y, and we have to substitute y equals to 0. So it will come out to be 2 u by delta. So you can equate both the tau, and integrating the right hand side and the left hand side. So at x equals to 0, delta is 0, and at any x, delta equals to some uh, variable delta. So we can integrate and solve it. So this is how we will get the expression of delta in terms of x, and we can replace this term with the Reynolds number. So delta will come out to be 5.477 by root of by square root of Reynolds number. Yeah. So now coming to the third problem, a viscous fluid flows past a uh, flat plate such that the boundary layer thickness at a distance 1.3 is from the leading edge is given as 12 mm. So at any distance x, the value of delta is given. So we have to find out the value of delta at different values of x, which are 0.2 meter, 2 meter and 20 meters. So in this problem also we have to assume the laminar flow. So moving to the solution. So delta we have uh, for the laminar flow we have read that delta by x equals to k times Reynolds number to, raised to the power minus zero point 0.5, and we can say that this delta is directly proportional to root x. So delta, we can assume it to be some constant c. So the value will remain constant for different values of x. So this x, the k viscosity in mu infinity will remain same for all these values of x. So we can take it as c, and we can find the value of c using the first um, data that is given to us, that is at x equals to 1.3 meter, delta will be equals to 12 mm. So the value of c will come out to be 1.05 times 10 raised to power minus 2. So in this way we can find out the expression for delta, and by substituting all these three different values of x, we can find the respective value of delta. So you can check your answer. So now quickly moving to the fourth problem. If the upstream velocity of the flow in the problem 3 is given as 1.5 meter per second, and we have to find out the kinematic viscosity. So yeah, so in the above problem, um, we know that from the Blasius solution, we can write delta equals to 5 times root mu times x by u. So we know that the value of c, that is 5 root mu by u. So we can find out the value of kinematic viscosity. So just make sure that you find out the value of kinematic viscosity, not the dynamic viscosity. So which is important here. Yeah, and please make sure that uh, you always write the final answer in SI units if it's not given. Or so depending upon the data, which is units which are given in the problem statement. So always mention the units at the end. So for the viscosity, it is meter square per second. So now moving to the last problem. Consider the laminar flow for an incompressible fluid past a flat plate at y equals to 0, and the boundary layer velocity profile is given to us, that is small u by capital U is equals to y times y by delta for y less than equal to delta, and the velocity will be equal to the free stream velocity for y greater than delta. So the velocity profile is shown in this figure 1, and we have to find out the shear stress by using the momentum integral equation, and we have to compare these results with the Blasius solution. So in this, it is similar to that of the that we solved in the second problem, that is the part B. So it's very uh, uh, both are like quite similar. So quickly moving to the solution. So the tau will be equals to mu times. So this is the velocity profile which is given to us. So tau equals to mu times du by dy at y equals to 0. So which will be equal to rho times u square d theta by dx. And by similarly writing theta as the integral y dash minus 1 minus y dash d by dash. So here the integral limits uh, will change from 0 to 1 after we substitute y by delta equals to y dash, and theta will come out to be delta by 6. So after differentiating both sides, d theta will be equal to d delta by 6. And substituting in the above equation, we can solve the delta in terms of x by integrating both sides, LHS in the RHS. And we know that at x equals to 0, delta will be 0. So the lower limit will be 0 on both sides. So delta will come out to be root 12 mu times x by u. So the final expression of tau will come out to be 0.288 times u raised to power 1.5 times root rho mu by x. Yeah, so using the Blasius solution, uh, this constant, the value of this constant was 0.332. So it is because the velocity profile here is assumed to be a straight line, so which is not the case in reality. So we can find out the percentage error, like difference between uh, um, so how our final results varies compared to the Blasius solution. So we can find out this percentage. So it will come out to be 13.2%. So I think that's it. So I will stop the recording here. And if you still have any doubts, so before major, you can ask, you can email us, or um, maybe we can organize one doubt session before major if you guys want. So I will stop the recording here.